breakdown of local effective field theory. Please, stage is yours.
Okay, so first of all, I'd like to thank the organizers, Shravan and Luca, for putting together a wonderful workshop. I've learned a lot by listening to all the discussions. Now, I feel a little bit awkward at giving this talk because all the talks that we've heard so far were very high level, quite technical. And my talk is going to be very low level. So hopefully I'll at least make it entertaining and maybe a little bit provocative. So this is the outline. And I want to start with the most robust part, which is the introduction. And I want to start again with the data, which you already saw from Alexei's talk. We have beautiful data, the cosmic microwave background map, which we've quantified. And this is the angular power spectrum of the microwave background. The temperature fluctuations, so the power on the vertical axis, the angular scale on the horizontal axis. And the data, which is a black dot, show these beautiful oscillations, acoustic oscillations. Now, as Alexei already mentioned, this is not a unique prediction of inflation. So I want to elaborate a bit on this, because some of you who work on quantum gravity may want to construct models of quantum gravity that do not contain inflation. And you will have to know what are the crucial criteria which your model will have to satisfy in order to agree with the data. So here is a poor representation of a figure which appeared in a 1970 paper by Zuniaev and Zeldovich. So the vertical axis is time. The horizontal axis is co-moving spatial coordinates. If you see my cursor, this is a time of recombination when the microwave background is released. And this diagonal black curve, this is the horizon before recombination. And as Zeldovich and Zuniaev argued, and parallel to them, Peebles and Yu, they said, given a roughly scale invariant spectrum of fluctuations, curvature fluctuations on these super horizon scales, they are frozen in until the wavelength enters the Hubble radius, then they will start to oscillate. And you see that different wavelengths undergo a different number of oscillations between when they start to oscillate and when they release the microwave background. And so some you catch at maximum amplitude, some you catch at minimum amplitude, and this is the physics that gives rise to the acoustic oscillations. So now the same figure in this 1970 paper contained a second part, which is the matter power as a function of wave number. And these oscillations in curvature also induce oscillations in a matter power spectrum. So given a roughly scale invariant power spectrum of roughly adiabatic fluctuations on scales, which according to standard Big Bang cosmology look super horizon before equal matter and radiation, such a spectrum was already known to give a good agreement with the power spectrum of galaxies. Then in 1970, the acoustic oscillations in the CMB angular power spectrum were predicted, and the baryon acoustic oscillations in the matter power spectrum were predicted. Now, the question that was not answered in 1970 is, how does one obtain such a spectrum? And indeed, inflation is the first scenario based on causal physics, which leads to such a spectrum as derived by Alexei and by Chibisov and Mukhanov. But it is not the only one. So what are the criteria which a successful all-universe scenario has to satisfy? Well, the horizon, causal horizon, has to be much, much bigger than the late-time Hubble radius in order for the scenario to solve the horizon problem of standard Big Bang cosmology. Then if you want a causal mechanism, a locally causal mechanism for the origin of structure, then fluctuations have to originate inside the Hubble radius at early times. And finally, if you manage to satisfy those two conditions, then there also has to be a mechanism to produce approximate scale invariance. Okay, and indeed, in inflation, these three criteria are realized. So this is a space-time sketch of inflation. So the vertical axis is time, the horizontal axis is space. The time interval between Ti and T sub r, that's the period of inflation, during which the Hubble radius, which is the inverse expansion rate, is approximately constant. So this solid blue line is the Hubble radius. And during this period of inflation, the horizon, the forward light cone, expands exponentially. So indeed, you see that the horizon becomes exponentially larger than the Hubble radius, and criterion 1 is satisfied. Now, if we trace back the fixed co-moving scale of cosmological fluctuations, so this red curve, we trace it back to the end of inflation, and we trace it back further, then you find that if inflation lasts long enough, then this scale, the scale corresponding to scales which we observe today in the microwave background, these scales originate sub-Hubble at the beginning of inflation. So criterion 2 satisfied. And the approximate time independence of this inflationary phase leads to the approximate scale invariance of the spectrum of cosmological fluctuations. Now, this is a second scenario in which all three criteria are satisfied, and this is a bouncing scenario. So the vertical axis is time, the horizontal axis is co-moving spatial coordinates. We start with a contracting phase in which the Hubble radius is decreasing. And then there's some new physics which gives us a bounce, a transition to expansion. And this is the Hubble radius during the phase of expansion. And these two vertical curves indicate co-moving scales of fluctuations. So first of all, you see that since time runs from minus infinity to plus infinity, the horizon is infinite. It's infinitely larger than the Hubble radius. Criterion 1 satisfied. Fluctuations start sub-Hubble early in the contracting phase. Criterion 2 satisfied. And well, there are various scenarios to satisfy criterion 3 as well. One of them is a matter-dominated phase of contraction, and the other one is the aquatic contracting phase. The third scenario is what I call the emergent scenario, in which you assume that there's a new phase. Maybe gravity doesn't even exist. Maybe space-time doesn't even exist. There's an emergent phase which undergoes a phase transition to standard Big Bang expansion. This T sub r, that's the time of the phase transition. And if this indicates the time evolution of a scale factor, then you get a space-time diagram, which looks like this. So time, space, and the blue curve, that's the Hubble radius. It is infinite in the emergent phase. Then it comes crashing down and expands like in standard Big Bang cosmology. Red is the wavelength of perturbation modes. They originate inside the Hubble radius, and they propagate outside, and we see them today. Now, to make contact with what Alexei mentioned, in this emergent scenario, you give up both inflation and the quantum origin of fluctuations, because in this scenario, you assume that fluctuations are of thermal origin. Okay, so these are three scenarios. And let me tell you just a little bit about the aquatic scenario. The aquatic scenario is a version of a bouncing cosmology, which is described by the Einstein-Hilbert action. You assume that there's slow contraction given by matter with an equation of state which has pressure divided by energy density much bigger than 1, which can be obtained by using a scalar field with negative exponential potential. So I'm sorry, you need, again, a scalar field like for inflation. Now, the advantage of having this slow contraction is that anisotropies are diluted, spatial flatness is created, and this is a global attractor in initial condition space. Large field inflation is indeed also an attractor in initial condition space. I'm not going to get into the debate whether it's global or local. Also, negative exponential potentials are ubiquitous in string theory. This is the first time in my talk where string theory arises. So now the challenge for the aquatic scenario is how to get a bounce. And how do we obtain a scaling down spectrum of curvature fluctuations? And do we obtain gravitational waves? And this is where non-locality comes in. Let's add a very simple ingredient to this aquatic scenario, to the effective action, which is Einstein gravity plus scalar field. Let's add this S-brane. This is an object like a topological defect, but it is space-like. It lives on a surface with constant string amplitude curvature. And this is well motivated from string theory. Well, if you assume the existence of such an S-brane, then you get a non-singular transition between contraction and expansion. You get a roughly scaling down spectrum of curvature fluctuations. You get a roughly scaling down spectrum of gravitational waves. Therefore, you can make connections with current observations. And to satisfy Richard, here are the consistency relations that you get. The tensor tilt is 1 minus the scalar tilt. So it's like blue tilt. And you get this relation between the amplitude of the gravitational waves and the amplitude of the curvature perturbations. Okay, so message from this first part of the talk is that we do not need inflation to make contact with observations. So now I'm going to be more and more less rigorous and more provocative. Now I'm going to try to argue that if you accept string theory, then you inevitably will have a breakdown of effective point particle field theory at high densities. Okay, so to make this point, I'll take a very pedestrian approach. I will take some background compact space, and I will just consider the new degrees of freedom and new symmetries which strings have compared to point particles. Well, strings have the usual center of mass degrees of freedom, but strings can also wind space, and the energy of the winding modes is parameterized in units, integers of the radius of the compact spatial dimension, whereas the energies of the momentum modes is parameterized in units of 1 over r. Then there are oscillatory modes. Infinite tower of oscillatory modes whose energy is independent of r. So new states and new symmetries. You have this duality symmetry. If you replace r by 1 over r and replace momenta with windings, then this mass spectrum of string states is unchanged. The interactions of strings is unchanged. And if you assume that this is a symmetry at the non-perturbative level, then you get this, then you predict the existence of D-branes. Okay, so if you now look at kinematics, if you plot the temperature of a string gas as a function of the radius, then you find that as you decrease the radius, the temperature initially grows, but it levels off. There's a maximal temperature of a gas of closed strings in thermal equilibrium. And for small r, the temperature comes crashing down because the energy flows into the winding modes. No temperature singularity. So if you now assume that there's some action which gives us the radius as a function of time, then we can translate this curve into a temperature time curve. And you see that you either get an emergent trajectory, the green, or a bouncing trajectory, namely the purple one. Okay. So far, non-locality has not entered, but let's now put in just very basic quantum mechanics. In quantum mechanics, you get position in terms of a Fourier transform of momentum. But in string theory, there's something which is similar to momentum, namely windings. So you can construct a dual position operator in terms of a Fourier transform of the windings. So you have 2 position operators for each topological dimension of space. Now, if your space is large, then the momentum modes are light. If the space is small, the winding modes are light. So a poor experimentalist who has access to a limited amount of money will be measuring length in terms of the position variables for large R, but in terms of x tilde for small r. And for r approximately equal to 1, which is string densities, both x and x tilde are going to be equally important, which tells me that at string densities, the usual effective field theory based on supergravity inevitably will break down. And if an effective field theory description is valid, it will have to be an effective field theory in 18 spatial dimensions, not 9. Okay, so this is the physical length operator. It never goes to 0. So you see that in string theory, you have the potential of singularity resolution. Okay, now going back to this picture and the resulting space-time diagram, if we now assume that it is thermal fluctuations of a string gas which operate in this phase, then we can make predictions for cosmological observations. And I summarize these in one slide. I could give a whole talk on this. So in this scenario, perturbations arise as thermal fluctuations of the string gas. The thermal fluctuations have holographic scaling, which means, for example, that the specific heat capacity goes as r squared and not as r cubed. And this leads to a scale-invariant spectrum of curvature perturbations and a scale-invariant spectrum of gravitational waves, and two consistency relations between the 4 basic cosmological observations. Again, you get a blue tilt for the tensors, and so this is approximately equal, and the second consistency relation is only of order of magnitude. So again, I could give a talk on this, but I won't. I'll move on to telling you a little bit about what one could obtain if one sticks to an effective field theory description, but one which is consistent with this T-duality symmetry and which therefore operates in 18 spatial dimensions, 2 times 9. So again, we want some dynamics. So the dynamics of space-time is should be consistent with T-duality symmetry. Einstein gravity is not. Double field theory, which we heard of a little bit from Olaf Holm, this is a model which is consistent with the T-duality symmetry of string theory. So if you do cosmology in this setup, then the space-time metric is given by this form. You have the scale factor for the usual spatial dimensions, and for the dual position operators, you have the inverse scale factor. So this is the metric for double field theory cosmology. There's also a dilaton. There's an action which reduces in the limit of large radius to supergravity. But this action will give rise to equations of motion. And the equations of motion for cosmology are the following. There's a dilaton equation of motion, a constraint equation, and a Friedman-like equation. We can couple a string gas to this background, a string gas which has an equation of state parameter, which is that of radiation for large scale factors, that of winding strings for small scale factors, and it interpolates between the two. So this is what this string gas matter equation of state parameter does. And then you can look for limiting solutions. So in the large radius limit, you get radiation, scaling of the energy density. Small radius limit, you get winding, scaling of the energy density. You look for power law solutions, scale factor and rescale dilaton. And then you can solve these equations in the Hagedorn phase, so intermediate between large and small scale factors. And then you find a solution which is static in the string frame, evolving dilaton. In the large scale factor limit, you get radiation with constant dilaton. And in the small scale factor limit, you get contraction and a time-dependent dilaton. So what do you get? You get a bouncing cosmology in the string frame, which is non-singular. In the Einstein frame, however, the scale factor does go to 0 as T goes to 0. So, well, what about singularity? Well, it looks like you might have a singularity in the Einstein frame. However, as t goes to 0, the energy in a string gas drifts to winding modes, and we should describe the physically measurable quantities in terms of winding mode states. And in terms of winding modes, it turns out that the time actually goes to -infinity as the Einstein frame time goes to 0. So even in the Einstein frame, you can argue that you get a non-singular cosmology. So this is now, if you stick to an effective field theory description, however, in the context of double field theory. So if this was not provocative enough, now will come the real provocative things. I don't really have time for this. I'll skip over this. Sorry, Helitze. Now I will argue that if you accept string theory, then you cannot even use effective field theory at energies which are significantly smaller than Planck densities. And there are two types of constraints that I'll talk about. One is a swampland constraint, and the other is Transplunkian cosmic censorship. And Sravan, please give me the 5-minute warning. So the swampland conjectures rely on string theory. The Transplunkian cosmic censorship conjecture is more general. So if we stick to low energy effective point particle field theory, there's a vast landscape. Any space-time dimension goes, any number of field goes, any shape of potential goes, any field range goes. Superstring theory is very constraining. Only one dimension works. All scalar fields have a geometric origin. The potentials in the low energy field theory are set by the string construction. So is the field range. So only a very small subset of effective field theories can be consistent with string theory. The rest lie the swampland. And this is this diagram which I stole from Aaron Palti. So you have this huge space of possible effective point particle field theories. You have this UV complete theory and these small habitable islands which stick out of this swampland. And what are the conditions for these habitable islands? Well, this effective field theory, any given effective field theory, can only be valid for field range, which is smaller than m Planck. And the potential of this scalar field obeys these conditions. So either the potential is sufficiently steep or sufficiently tachyonic. Now, anyone who's worked on inflation will realize that these are exactly the opposite conditions to the conditions that you need for canonical slow roll inflation. And if you want inflation to be an attractor, then you also need large field ranges. Okay, so if you buy the swampland criterion, there's no canonical single field inflation, there's no eternal inflation, there's no bare positive cosmological constant. Applied to present day cosmology, dark energy cannot be a bare cosmological constant, and quintessence is constrained. It is not, you cannot just construct an arbitrary quintessence potential. Your quintessence potential has to be sufficiently steep. It is still consistent with observations as shown in this paper. Now, I hope that future observations are going to rule out any quintessence model with a reasonable potential. And that will tell us that dark energy gives us really important information about quantum gravity. So now, the last point that I'm going to mention, the Transplunkian censorship, is independent of string theory. So this is a space-time diagram of inflation, which I showed you before. And the big success of inflation is that the physical wavelength of modes that we see today is exponentially amplified during the phase of inflation. And so if inflation lasts a long time, then the scales come from the Transplunkian region. So Bedroya, so there are obvious potential problems associated with this. And Bedroya and Waff very recently postulated that there should be a no-go theorem, a censorship criterion, which says that in no cosmology, Transplunkian modes ever exit the Hubble radius. So no mode whichever was Transplunkian can ever exit the Hubble horizon. So if this is the way we parameterize the background metric, the Transplunkian cosmic censorship says the following. You start at time t sub I with a Planck length. You evolve until time t sub r, and you're bound to remain with a physical wavelength which is smaller than the Hubble horizon at time t sub r. So this, what I'm circling, is the mathematical form of this Transplunkian cosmic censorship conjecture. Now, one justification for this is in analogy with Penrose's cosmic censorship conjecture. So Penrose says that, well, if you consider black holes with charge smaller than the mass, there's a singularity, but the singularity is hidden from the observer by a horizon. So the observer outside of the black hole never sees the bad things associated with the singularity, never sees the non-unitarity. However, Einstein's equations, the low energy effective field theory, admits solutions with charge greater than the mass. And for those solutions, the observer at infinity would see the singularity, and this would be a fatal problem for causality. So Penrose says, paraphrased, the low energy effective field theory of gravity admits pathological solutions, but the full theory will not admit pathological solutions. So this is what I wrote down here. So this is the conjecture. So now let's take Penrose and let's translate. We first translate position space to momentum space. The singularity of a black hole becomes the Transplunkian region of modes. The black hole horizon becomes the Hubble horizon. And then Penrose, paraphrased, would say that the observer who only has access to modes with wavelengths larger than the Hubble radius must be shielded from Transplunkian modes. Why the Hubble horizon? Well, people who've worked with cosmological perturbations will know that perturbations only oscillate on sub-Hubble scales, and they only freeze out and become squeeze states and classicalize on super-Hubble scales. So a very conservative demand is to demand that the classical region be insensitive. The classical region, the region which is super-Hubble, is insensitive to Transplunkian region. Now, another justification is the non-unitarity of quantum field theory in an expanded universe. Naive quantum field theory, point particle quantum field theory. So this was already discussed in 1985 by Nathan Weiss. So if you take the Hilbert space of an effective field theory, it's a product Hilbert space of all momentum modes. Well, the momentum modes are co-moving. If we want to maintain a fixed physical ultraviolet cutoff, we have to create modes as a function of time. This is obviously extreme non-unitarity, and we would like observations to be shielded from this non-unitarity. And this tells us that no Transplunkian modes ever exit the Hubble horizon. So now if you accept this Transplunkian censorship, what does that imply for inflation? So this is a space-time diagram of inflation where I've shown the Transplunkian censorship to be marginally satisfied in the sense that the Planck length at the beginning of inflation becomes exactly equal to the Hubble horizon at the end of inflation. So inflation cannot last longer than I've drawn in order to be consistent with the TCC. However, if we want to explain the origin of the microwave background fluctuations with inflation, then the current Hubble radius has to be smaller or equal to the Hubble radius at the beginning of inflation. And I've shown this criterion to be marginally satisfied in this space-time diagram. Now, the location of the Hubble horizon depends on the energy scale of inflation. The higher the energy scale of inflation, the closer this Hubble horizon goes to the Planck length. And so demanding that inflation be consistent with the TCC and give an explanation for structure formation in the universe gives an upper bound on the energy scale of inflation and a simple calculation, which is this TCC bound and this bound for successful structure formation, tells us that the energy scale of inflation has to be this low, lower than 10 to the 9 GeV, which implies that the primordial tensor to scalar ratio, if you manage to produce scalar fluctuations, is smaller than 10 to the minus 30, which means that obviously the secondary tensors will be much larger than the primary tensors. So, again, it means that standard canonical slow roll inflation simply is inconsistent with the TCC. Now, what does this imply for dark energy? Well, dark energy cannot be a bare cosmological constant. And the good news is that our universe will not end in a singularity. Okay, so I still didn't get the 5-minute warning.
Yeah, well, you said 5 minutes already before, so I didn't.
Okay,
mention.
so
Yeah,
anyway, so the robust thing that I tried to convince you of is that data does not require an initial period of cosmological inflation. And so therefore, for those of you working on quantum gravity, you don't need to force inflation into your theory. Now, the rest is more provocative. I was arguing that string theory inevitably leads to a breakdown of effective field theory at string energy scales, or maybe lower. And quantum gravity more generally constrains low energy effective field theories. And inflation does not naturally emerge from superstring theory, at least inflation constructed in a perturbative setting. So just to, so this doesn't tell you that you cannot construct inflation non-perturbatively. And there's indeed evidence, both from Ghia's work and also from work by Keshav Dasgupta and his collaborators at McGill, that you can construct inflation as a coherent state about Minkowski. But inflation is still fine-tuned, assuming the validity of the TCC. And again, these non-perturbative constructions of the zeta seem to be consistent with this. Some alternatives to inflation are consistent with these criteria. And so my most provocative conclusion is that alternatives to inflation appear to be more promising than inflation in light of fundamental physics. So hopefully I've been provocative enough to have generated some questions.
Thank you very much for Robert for the very nice talk. So we have time for a couple of quick questions, then we will continue if there are any rest in the discussion session. First, Anupam, please unmute and ask. Yeah.
Thanks, Robert, for a wonderful talk. So it's very nice, very provocating. So I have a question. So since you're pushing for this quantum gravity approach, which is very nice. But then in this approach, what exactly do you mean by the beginning of the universe? Or, how would you then define your even time? So even I'm struggling with the fact that, where do you start here? Why do you even consider about the singularity problem?
Well, what I'm saying is that in this setup, I seem to be able to take some conditions, some Cauchy conditions, and I seem to be able to evolve arbitrarily far into the future and arbitrarily far into the past. And I'm avoiding answering your question, Anupam, because I can't. There's a philosophical problem. Like in the standard Big Bang setting, I cannot answer the question, what is T equals 0? So in my opinion, there'll always be, so my view is that I take some conditions at some fixed time, and I evolve both into the past and into the future.
Okay. Thanks.
Next question is from Gia. Please unmute.
Hi, can you hear me?
Yeah, I can hear you, Gil.
Hi. Yeah, Robert, thanks for the talk. And I just have okay, we can discuss endlessly, obviously. I don't want to cross over into the discussion session. Maybe we can also continue later. I have, so you showed these consequences from the string theory. You had a list of consequences in one of those slides. So except
the perturbative.
Yeah, first was absence of single inflaton, and then there were other consequences like absence of lambda and so on. The constraints on slow roll and so on.
Okay, yeah.
Now,
yeah.
So except the first one, which I don't see how, yeah. So except the first one, because first one, I simply don't have enough evidence. So therefore I cannot claim that there is something like this coming from string theory. But all the others essentially were derived in our original paper from 2013, from the S-matrix perspective.
Yeah, I agree with that. I agree with that, Gil.
Right. So then the thing is, now you see, somehow these are extremely important issues. Of course, many people may disagree with us, etc. So it's very important to clarify. Now, the one thing that I find a little bit confusing in this discussion. So when things are predicted from microscopic theory, so either we have to discuss within microscopic theory and point out if there is some disagreement or mistakes, or we should come up with some alternative microscopic theory. Because if we simply conjecture things that part of which already has been computed in microscopic theory, but then there is another part which sort of is not obvious, okay? I don't see how to progress at the level of conjectures. You see, this is my problem. Because I think it's, and I don't know, this is a general remark that I think it's very important to appreciate the importance of microscopic theory and rigorous computations, because they then tell us, I mean, it's fantastic to make conjectures. I have nothing against conjectures, but you see, also must be confronted from what microscopic theory is telling us. In other words, to give you an example, for example, we cannot, it would be counterproductive to conjecture Fermi theory after standard model has been invented, right? Because standard model allows us to compute Fermi operator with a very specific coefficient. Now, if we say, oh no, we don't care about standard model, let us conjecture Fermi operator, that's okay to do before the standard model. But after the standard model, if we're conjecturing something that has a different coefficient, we have to justify. In other words, we have to then come back and say, no, standard model is not correct because of this and this and this, and we have some alternatives. So that's my comment. So
can I cut you off here? Yeah,
sure.
Because I sort of agree with you that once you set up these challenges, then you have to go on. And you know me, Gia, I'm interested in developing these alternatives. So I completely agree with you that we should not rest here with these conjectures. Now, what I try to show is that if you work in the context of effective field theory, then you're doing something which is inconsistent.
No, I'm not working. I'm working
I know that you're not. Many people are.
String theory. So that's why I think I'm on the right track. As long as S-matrix is concerned. So no, I don't want to debate. This is not about debate. We can continue that later during the discussion session or even later, even after that. I'm just saying that there must be the productive framework would be to find touching points. And then when something has been predicted from microscopic theory, if conjecture mostly agrees with it, but slightly disagrees, then we have to go back and see what is that we were missing in microscopic theory, if there was not correct. So that's what I'm saying. Anyway, we have an intersection on 4 points. We fully agree on 4 points out of 5. So that's already a good point. Yeah, good.
Yeah, no, I agree with you. Now, let me give you a challenge, Gia. The thing that I have not seen in your approach is how do you justify, how do you get this initial de Sitter state?
I propose let's discuss the challenges in the discussion session.
Yes, we can continue on discussion session. Yes, thank you, Robert.
Discussion session. Yeah. Thank you very much, Robert. Thank you very much for the talk. And let's also